Hi, I'm Joanne Rhodes, and today I'm going to talk about Sir Isaac Newton's universal law of gravitation. He was really an amazing scientist, and when he was home for a year and a half because of the plague, he came up with just about everything that he's famous for today. So as you can see on the slide, we've got his universal law of gravity. The equation is telling us the size of the force due to gravity between two masses, any two masses in the universe, m1 and m2, separated by distance d, and it gets squared. G is just a universal constant. It's a constant, so it's always the same no matter what two masses and distance we're using. He worked on this for quite a while. It's a very powerful equation. It's got a lot of information embedded in it. When we talk about Kepler's laws, those orbital laws of Kepler's can all be derived from Newton's universal law. It gives us possible orbits of a circle, an ellipse, and a circle is a special case of an ellipse. It also can give us a parabola and a hyperbola. All of that is embedded in here. All of these shapes are actually sections of a cone. So if I draw just any cone, like an ice cream cone or a styrofoam cone that you could actually cut, if you were to cut parallel to the top face, you would get a circle. If you were to cut at an angle, you would get the shape of an ellipse. If you were to cut parallel to the central axis, you would have a parabola. And if you cut parallel to the wall of the cone, you get a hyperbola. So all of those are possible orbital shapes that we might end up with. And I'm going to go ahead and tell you about some are bound, some are unbound. So these are bound because they repeat, and these are unbound orbits. They would correspond to something coming in and leaving and never coming back. So Newton had actually a friend named Sir Edmund Halley, and Halley was very interested in Newton's work with gravity. And Halley was looking at comets and when comet sightings had occurred. No one had ever before Halley said that they thought that one comet was returning again and again. And he found some comet sightings that indicated a pretty regular repetition period if it were the same comet. He said, I think that is all the same comet, and it was a period of about 78 years, and he predicted when that comet would return. He did not live to see it, but he did predict it, and it did come back. So it was called Halley's Comet, and that is the most famous comet. It has an elliptical orbit, so it is that it has to have one of these if it's going to keep coming back. Let me go ahead and show you what Newton came up with to describe orbits. He started with just falling objects, like an apple from a tree. And he's the first one we know of that connected a falling object to an orbiting object. He said, I think it's the same force. I think that the same force that makes an apple fall to the ground is also making the moon go around the earth. And he said, imagine having a cannon on top of a mountaintop and firing the cannonball at different speeds. That would give the cannonball different amounts of energy. So if we do that, if we fire the cannonball at, say, 1 kilometer per second, it would go a certain distance and then hit the earth. Notice that if the Earth were flat, it would have hit right about here. Instead, because it's round, it hit right about here. Now, let's turn up the speed. When we turn up the speed, we're adding kinetic energy. So now if I turn it up to 2 kilometers per second, the cannonball hits further away. I'm going to jump up to 4. And each time I give it more energy, the cannonball goes a little bit further around the Earth. But it's just a falling object. If I keep doing that, eventually it's going to get all the way around and we'll have an orbit. So the difference between a falling object and an orbiting object just has to do with how much energy it has at launch and how big the planet is that it's trying to go around. So at 8 kilometers per second, we've got a circular orbit. So this is just a falling object, but it never hits the Earth. What happens if I give it even more energy? I'm turning it up to 9 kilometers per second, and now I've got an ellipse. It's going to take more time to go around the Earth than it did before, but it's still a bound orbit. I'm going to go to 10 kilometers per second, and it's a bigger ellipse. It's going to take longer for it to go all the way around, but it's still a bound orbit. And if I wait long enough, we'll see it come back. There it is. It's going to come back, and it's a repeating orbit. Now if I go up to 12, we've given it even more kinetic energy, and it's never coming back. We've exceeded the escape velocity of Earth. So now we've got either a parabolic or a hyperbolic orbit. It's just one pass. Okay, and let's see. The last thing I'm going to tell you about it is that this is just a special example. This has to do with orbits and energy. So if we had, pretend we had a hyperbolic orbit for a comet, so it was only going to come around one time, but it happened to go to near Jupiter and had a gravitational interaction, so we'd have the comet as one mass and Jupiter as the other, and they're close enough that they are going to exchange some energy. So as a result of the gravitational encounter, the comet goes into an elliptical orbit, and then it's captured. It's just going to have that repeating orbit. So it lost energy. It lost energy. If it goes from an open orbit to a closed orbit, it's got less. Where did it go? It had to go to Jupiter. We don't just have energy disappear. And so Jupiter is going to have a little bit more energy as the comet has less. That's it.